Hello guys. In today's video we're going to be looking at what's called lattice energy. Lattice energy, we're going to define what it is and discuss the trends within lattice energy, and we're going to draw what's called a Born-Haber cycle and use it in order to determine our lattice energy, energy of formation, electron affinity, and ionization energy. So we're going to relate all of our energies that are included in ionic bonding. So all of these energies are included when we consider ionic bonding. When we talk about our lattice energy, it's basically describing the stabilization that is gained by arranging ions into a lattice. So having a repeating arrangement of cations and anions, um, how stable that is versus the free ions themselves. It is defined as the energy required to completely separate 1 mole of an ionic compound into its composite gaseous ions. So if we have something like sodium chloride, breaking it down into gaseous sodium ions and gaseous chlorine ions. So taking those two gaseous species and combining them gives us our lattice energy. And in the case of sodium chloride, that is 788 kilojoules per mole. So pretty significant. Okay. And if we are forming our ionic compound from the gaseous ions, we would just reverse the sign of everything. Okay. Now, keep in mind some things when we're talking about our ions or our lattice energy. When we are looking at the ions themselves, they're in the gaseous form, so they're going to be infinitely far apart. So there's no attractions or repulsions between the ions. And then as we form them into a solid compound, they are all together and they have those attractions between cations and anions going on. So it's not only just forming the ionic bonds, it's also the attraction that results from having those ions in close proximity to each other. That is completely devoid in the gaseous form itself. So gases are infinitely far apart. The gas particles themselves. And that means we have no attractive and repulsive forces between them. So basically, our electrostatic potential energy is equal to 0 because they're infinitely far apart. So that distance would be infinite. So it would be a 0. Okay, here are some common lattice energies within the first couple rows. And generally, when we look at our ionic compounds and the lattice energies, we will have a lot of the halogens, right, our salt forming. Even more over here. And then we have a couple of oxides and a nitride compound as well. Looking at these lattice energies, we can see some trends forming. So one, we're going to look at our cation size. Then we're going to look at our anion size. We're going to look at our charge, and we're going to relate all of this back to our electrostatic potential energy. So first, as we go from lithium to sodium to potassium to rubidium to cesium, we see that our lattice energy decreases. So it depends on the size of the cation. Then going from fluorine to chlorine to bromine to iodine, the lattice energy decreases. So it depends on the anion size. And then it also depends on the charge. So the magnitude of the lattice energy depends on ion size and charge and ion arrangement. But we're not really going to talk about that. It's just another thing that our lattice energy depends on. So lattice energy decreases as ion size increases. And then lattice energy increases as ion charge increases. And both of these things can be described by our electrostatic potential energy, where we have our constant, our charge on particle 1, charge on particle 2, and our distance. So the greater the charge, the greater the magnitude of the charge, the smaller the distance, the greater electrostatic potential energy, and lattice energy is going to be directly proportional to our electrostatic potential energy. Let's look at the energies that are related to ionic bond formation. There's a lot of different energies that are going to be going on, including phase changes. So we have enthalpies of phase change. Enthalpy of phase change. So going from solid to liquid, liquid to gas, or solid to gas, because we need all of our species, our metal and our non-metal, to be in the gaseous phase. So getting the metal and non-metal into the gaseous phase. And this is due to ionization energy and electron affinity. Okay, so remember our definitions there. This is going to be endothermic. This is going to require energy. Then we have enthalpy of dissociation. We're going to be starting out with elemental forms, and we'll go through all of these. But when we think about going all the way from our elemental form to our compound, which is what we're talking about when we're talking about going and forming ionic compounds, we need a lot of times to break apart diatomic molecules, such as chlorine gas or bromine liquid. All of these halogens are diatomic. So a lot of times we'll have to break them apart, or oxygen will form. Ionic compounds, so we have to break that apart. So a lot of times we'll have diatomics we need to break apart into atoms. So this is going to be the energy required to break apart diatomic molecules into atoms. Okay, this is also going to be endothermic. It's going to require energy. Next, we have our ionization energy. And this is going to be the energy to form the cation. So removing electrons. This also is endothermic, so it requires energy. As a note, the definition here, so a reminder of the definition, it is removing an electron from a gaseous atom or ion, which is why we have to be in the gaseous form for everything. Next is our electron affinity. And that's the energy associated with forming the anion. So adding electrons. Okay. And this is usually exothermic, but sometimes endothermic. And again, when we think about the definition here, this is going to be adding an electron to a gaseous atom or ion. Okay. And then our last two, lattice energy. We've already talked about this one, but it's energy of formation of the solid compound from the gaseous ions. So the energy associated with the formation of the solid ionic compound from gaseous ions. Remember lattice energy? If we are talking about forming the solid compound, this is going to be exothermic, very exothermic. If I had written it the other way, where we're breaking the solid compound into gaseous ions, that would be endothermic. But when we're thinking about it in the way that we're about to in just a minute, using our Born-Haber cycle, we think about it as an exothermic quantity. And then our last energy is our enthalpy of formation. So this is kind of the overall change associated with the formation of an ionic compound. So if we were to take all of the different ones we've just talked about a minute ago and combine them together, this gives us our enthalpy of formation, which is where we have our elemental forms combining to form our compound. Elemental atoms or molecules combining to form a compound. Okay, and this is going to be either exothermic or endothermic, depending. So it could be exothermic or endothermic. So we use what's called the Born-Haber cycle to visualize all of these energies. And I have a Born-Haber cycle for sodium chloride over to the side. So we can kind of zoom in on this and see what's going on. So we start out with our solid ionic compound down at the bottom. And then on our left side, we have anything that's endothermic. On our right side, we have anything that's exothermic, usually. So the first thing we have in here is our formation energy. So going from our um, elemental forms to our solid. This is one where it could be exothermic or endothermic. Usually it's exothermic, the formation itself, but the way that it's written here is a endothermic process because it's going from the solid to this species right here. So going from our solid to this species is written the opposite way that we usually write our formation energy, which is why it's a negative value. And then going from our species here up to our next portion up here, we see we're going from a solid sodium to a gaseous sodium. So that is sublimation energy, okay, which can also be written as the formation of the sodium gas. And then going from this next tier up here, we go from our diatomic species to our monoatomic species. So this is our dissociation energy, which can also be the formation of the chlorine gas. And then going from this tier up to this highest tier, we're going to have our sodium gas going to a sodium ion. So that's our first ionization energy. And in that process, we produce an electron, right? And then that electron is taken in by the chlorine in an exothermic process, which is our electron affinity. And then lastly, we have our lattice energy right here. Lattice energies are reported as endothermic processes. So when we are going in this direction, we are basically taking the negative of our lattice energy because we have our ions forming our solid compound. So it just depends on how you describe it. So in this particular example, there's the negative of both the formation and of the lattice energy. So it just depends on how you're going to write it. Okay, so we can use this Born-Haber cycle to determine any of the energies on the last slide. The Born-Haber cycle can be used to determine any of the energies that I just mentioned. So let's actually try an example of determining energies within a Born-Haber cycle. So let's make a Born-Haber cycle and look at the energies themselves. So we want to calculate the lattice energy of calcium chloride using a Born-Haber cycle. We are given these energies. So our first one, the enthalpy of formation of calcium chloride, that is calcium solid plus chlorine gas forming calcium chloride solid. That's our delta H of formation. And it's equal to negative 795 kilojoules per mole. Then we have our enthalpy of sublimation of calcium. So that's going from calcium solid to calcium gas. And that has a sublimation energy equal to 178 kilojoules per mole. And then we have our first ionization energy. So that's taking our gaseous calcium, removing one electron. So that's our delta H, first ionization energy, and that's equal to 590 kilojoules per mole. Next is our second ionization energy. So taking that calcium plus and removing an additional electron. And at this time, we have two total electrons. So that's our second ionization energy. And that is 1145 kilojoules per mole. And then our enthalpy of formation of chlorine. So this is 1/2 Cl2 gas goes to Cl gas. Okay, so this is for one atom of chlorine. Keep that as a note. You have to pay attention to how things are written. So this is our enthalpy of formation of chlorine. And that's going to be equal to 121 kilojoules per mole. And then the electron affinity, that's taking one chlorine in the gaseous phase, adding one electron to produce one chlorine ion in the gaseous phase. And that's our electron affinity of chlorine. And that's equal to negative 349 kilojoules per mole. So we need to take into account how much of everything we have when we're doing this. Now, all of these are going to go into our Born-Haber cycle. So I'll go ahead and give myself lots of room for that. We're going to start down at the bottom. And this is going to be our calcium chloride in the solid state. On our left side, we should have our formation energy. On our right side, we should have our lattice energy. And you can do this in a multitude of different ways, but I'm going to follow the same format that we saw in that figure above. So we're taking our calcium chloride and breaking it down into calcium in the solid state plus chlorine in the gaseous state. This is our negative R of our formation of calcium chloride. Right? So we're writing it as an endothermic process, which here we see it is an exothermic process. The next thing I like to write in is my lattice energy, and that's what we're actually solving for. So our lattice energy, remember, it's our ions in the gaseous state forming our solid or the other way around. So the actual definition of lattice energy is taking that solid compound and breaking it down into ions. So it's going to be the negative of the lattice energy. So negative delta H, lattice energy of calcium chloride. So here we've got our 2 plus calcium in the gaseous state plus 2 chlorine anions in the gaseous state, and they're going to combine to produce our calcium chloride, which is going to be exothermic the way that it's written. So anytime we have an up arrow, it's endothermic, a down arrow is exothermic. And then we're just going to go through going from our calcium solid, we need to get to calcium 2 plus gas. So the first thing we want to do is we want to sublime it. And this gives us our calcium gas plus chlorine gas. Then we're going to go from our calcium gas to calcium 1 plus. So our first ionization energy to form calcium plus chlorine plus 1 electron. And then our second ionization energy giving us calcium 2 plus chlorine plus 2 electrons. Then we're going to dissociate or form our chlorine atoms. So this is going to be 2 times our formation energy for chlorine, right? Because that's for 1 atom, we need 2 atoms. So this gives us calcium 2 plus 2 chlorines, and then we have 2 electrons. And then from here, we can go down with our electron affinity of chlorine. And again, we're going to multiply this by 2 because we have to do it for each of our chlorines. And that is our Born-Haber cycle. When we solve for our actual energy, all of our energies are going to sum to our formation energy. So our delta H of formation is going to equal our sublimation energy for calcium plus our first ionization energy for calcium plus our second ionization energy of calcium plus our dissociation energy or formation energy of chlorine times by 2 because we have 2 chlorines plus our electron affinity of chlorine times by 2 because we have 2 chlorines, and then lastly plus our lattice energy. Okay, so let's put all these values in. So we've got our enthalpy of formation, negative 795 kilojoules per mole. Note that we're just putting in our regular formation energy and our regular lattice energy. Okay, and it's going to be equal to our sublimation of calcium, which is 178 kilojoules per mole, plus our first ionization energy, 590 kilojoules per mole, plus our second ionization energy, 1145 kilojoules per mole, plus our formation of chlorine. We need to multiply by 2 for each chlorine. So we have 121 kilojoules per mole times by 2. And then we add that to our electron affinity. Again, we have 2 chlorines, so we need to multiply our electron affinity at negative 349 kilojoules per mole times by 2. And then we have our lattice energy. So our lattice energy here is going to be a negative value. Okay, so it's going to give us our lattice energy in the terms of combining the ions. So when you're looking at your sign here, keep in mind what these energies mean because they give some weird energies sometimes. So when we calculate this all out together, we get a lattice energy equal to negative 2,252 kilojoules per mole, which means we take our calcium 2 plus ions plus our 2 chlorine minus ions in the gaseous state to form calcium chloride in the solid state that has a lattice energy equal to 2252 kilojoules per mole. Okay, that is everything for this video. I hope you guys understand everything a little bit better, and I will talk to you guys later.